Welcome back to Topic 3, Convolutional Neural Networks. We'll continue this discussion about convolutional neural networks and its uses in processing images. So in the previous lecture, we talked about the most complicated layer, which is the convolutional layer, which acts like a kind of stencil or filter that detects certain shapes or characteristics in the underlying input features or the input pixels that we have. The next few layers are also part of the feature extraction layer, but they are much more easier to understand compared with the convolutional filter layer that we talked about in the previous lecture. The first one is basically the activation layer or the rectified linear unit layer. So just as in the conventional neural network, this ReLU or rectified linear unit layer is part of the neuron operations, and typically it's not really a separate layer of neurons, but it's actually integrated together with the way each layer of neurons work, just like a normal activation or thresholding function. However, it's not in most APIs related to neural network, the activation layer is given treatment as though it's a separate layer, and it's normally represented separately. So just bear in mind that in the actual the actual architecture, it is actually not really a completely independent layer, but it's actually part of the same summing layer of neurons that we have with the convolutional, or rather it just works together with the convolutional filters that we have been talking about earlier. Okay, we are drawing it separately as a layer, but in reality, it's actually part of the neurons layers that's part of the convolutional layer earlier. So you can think of it as a convolutions dash rectified linear unit function is together. And when we are defining it in Keras API, you find that actually the activation layer is just defined or specified as part of the definition for the convolve 2D API call. So you don't actually need to specify separately as an independent layer. However, the next one that we'll talk about, the pooling layer, is different. Now it's not necessary that a convolution and dash rectified linear unit is always followed by a pooling layer. You can have two convolve rectified linear units in tandem, that means next to each other, followed by a third layer that is actually a pooling layer. And we'll see this in some of the common architectures later on. So what is the purpose of the pooling layer? Now the pooling layer is basically inserted after the convolutional filters, and what its main purpose is actually to reduce the number of pixels. It's a compression layer. So every 4 pixels is reduced in size by 1/4. So 4 pixels is actually reduced in size by half along the width and along the height as well. So when you have a 2x2 pattern being reduced or downsampled down to 1, this actually results in a quarter size it actually reduces the size by 75%. So you only have 1/4 of the original data still remaining. Because 2x2, if you reduce it to one single pixel, basically it's just 1/4 of the original size. This downsampling may cause some concern that you may actually be losing important information, but think of it this way: when you actually have a shape in the image, even if you were to reduce the size by half, typically you can still recognize the shape. So if it's a round shape, if you reduce the size by half, it's still recognizable as a round shape. It's only when you do this to the extreme, that means you reduce it down to one single pixel or 2 pixels only, then obviously you have lost too much information. So you cannot have too many pooling layers. Okay, depending on your original image size, you shouldn't reduce it down to a level that you cannot recognize what the original image was. Okay, so there's a limit to how much pooling you can actually do. Now there's two main ways of doing the pooling, how you do the reduction from a 4x4, 2x2 to a 1 pixel. You can either use, typically you will use the max operation. It means you take the largest value or the max value out of these 4 pixels and use it for the single pixel that you reduce it to. And this is what we call a max pooling layer. It's actually one of the most common. You can also use other ways of doing this. For example, you can use the mean pooling. That means you take the average value of the 4 pixels and use it for the resultant pixel. So in the next diagram, we'll see what a max pooling does. So if you take a look at the diagram on the left, you see that it's a 224 by 224 pixel slice. When you downsample it by half on the width and length axis, basically it goes down to 112 by 112. And how we achieve this downsampling is that if you look at the diagram on the right, for every single 4 by 4 pixels, for example, the top left hand corner is the 1156, 4 by 4 pixels, right? 3 by 3 pixels. So my correct, I stand correct. 2 by 2 pixels. The top left hand corner, 2 by 2 pixels, 1156. Now we will take the maximum of all these 4 pixels, and basically you can see that on the right hand side, the largest value is actually 6. So the 4 pink 2 by 2 squares now get reduced to one single pixel of size of value 6. Which this is max pooling, so we'll take the largest value. Now similarly for the green for 2 by 2 pixels, you get 2478. The largest value is actually 8, so we reduce this to the value 8. Similarly for the orange one, for the yellow one, we reduce it to 3, and for the blue one, we reduce it to a value 4. So now the size actually basically is reduced by 1/4 from the original size. Now the last few sections of the convolutional neural network is just a normal multi-layer perceptron, what we call a fully connected layer. So this last output portion is just the normal classifier that we get. So the first few sections, the convolutional layer, the pooling layer, and the rectified linear unit activation functions, they help to extract the features. They basically try to detect what is some of the shapes that are significant from at the lowest level, then in the middle level, and at the highest level as well. And after it has detected all those relevant features or done the feature extraction in those convolutional layers, it then passed on to this what we call the densely connected or fully connected layers, which is just a normal regular neural network, which does the usual thing, right? Matrix multiplication followed by an activation function. So let's take an example of how this works out. So we are trying to recognize the image on the left, which whether it is a car or some other object like a truck, an airplane, a ship, or a horse. So you can see that the first convolutional layer closest to the input, you can actually recognize what comes out after the filters are applied to it. So the shapes is still recognizable. So each of these filters are basically recognizing different aspects of the car. It could be the bonnet, it could be the wheels, it could be the roof of the car. But you can still sort of distinguish what is actually originally in the image. Now after passing to the rectified linear unit, which basically runs through a non-linear function, so it will enhance some of the features that's actually looking at, you will then pass on to another layer which then recognizes higher level details, right? Higher level features, more abstract level of the features. So the first few layers recognize the most basic features. Then the deeper that you go, you will start recognizing more and more abstract features in the image. So as you go deeper and deeper down, you will notice that actually the image activation map that's being shown, right, is harder and harder to recognize what's actually in the original image, because it's actually a more abstract interpretation of the original pixel. So they've sort of been mashed around, right, by the filters that we applied, the multiple layers of filters or stencils that we applied to it. So you only the first few layers is where you can actually see the original image, but once after a few more layers of convolution, you can't really recognize the original shape of the car from the activation map anymore. And as it goes closer to the final layer, the fully connected layer, you can see that it is basically very, very abstract. Really, you cannot recognize the original car. So passing through the basically after going through all these multiple layers of convolution and pooling, you have sort of reduce the original image to a number of features, okay, or engineered features. Okay, in this case, it's engineered not by human but by the convolutional neural network. Now, these features basically forms a vector of values, right? And this just passed on to the fully connected layer, just like you would pass any other data sample row or vector into a normal multi-layer perceptron in order to classify it. In this case, this is a multi-class classification because there are 5 output classes possible: car, truck, airplane, ship, and horse. Now, it has been trained to determine that the most likely image that is being presented to the neural network is actually a car, which is why the green bar is the largest. It still has a certain detection probability that it's a truck, but it's much lower than the probability that it is a car. So I hope this particular diagram gives you a good summary of how the different layers that we've been talking about sort of come together to work. So the first few layers, let me repeat, are trying to basically extract out the features. So starting from the lowest level, most basic features, so it's very closely related to the original image. Then as you go deeper and deeper into the mid levels and further into the network, you start abstracting out more and more abstract features, which are combinations of the lower level features. So by the time we come to the fully connected layer, typically you cannot recognize the original car image in the activation map anymore. So people have been trying to debug convolutional neural network, so they've devised various techniques to sort of visualize what is coming out from the convolution layer so that they can see which features or which part of the image is the neural net actually focused on, because sometimes what is being the good thing about feature extraction is that it's automatic, right, in the CNN, but the bad thing is that the neural network may not be focusing on the things that you as a human would be focusing on. So there's this well-known negative example of CNN being trained to recognize wolves and huskies. Okay, the wolf and huskies, one is a wolf, a wild animal, and the other one is a dog, a husky. And it seems that oftentimes the wolf and husky was not correctly identified with the neural network. So they were wondering why the husky was always identified as a wolf. So running through one of these debugging tools, they realized that actually contrary to what the human would expect, when we try to recognize the wolf and the husky, it was actually looking at the background of the image. So because both the wolf and the husky were photographed in a snowy background, snow, right, it's white in color, so the neural network was actually focused on the snow. So every time it sees the picture with a husky in it, and the husky also happens to be in a snowy background, it recognizes it as a wolf instead of a husky because of the background and not because of the shape of the dog itself. So this actually just highlights the really big need to not just take the training for granted. You may not be focusing on the things that you think you should be focusing on. So you need to do some debugging. So one common way to look at the debugging information is to look at the image as it comes out from the activation map. That means after it goes through the convolutional layer and it generates the activation map, you take a slice of each of the filters output and you see what is the kind of shape that the filter is actually detecting at different layers. So you can see that from the original layer of images, layer 1, you can still see distinct shapes in the activation map. But by the time you come to layer 2, it gets a bit more blurry or more abstract. It's harder to recognize. And the one on the right is the original images. The original images is crystal clear and sharp, and you can see there are different patterns in the original image. But after it goes to layer 1, it's sort of abstracted. You can see that especially the top left-hand corner, there are some very distinct diagonal lines, right? So it's sort of recognized by the filter as well, all those strong diagonal lines. But by the time you come to layer 2, the top left-hand corner, you can't really understand what is actually being detected anymore. But it does give you, you can still see that actually the focus, even at layer 2, is all these diagonals, because you can see some diagonal shapes in there. So this is what the filter is actually focusing on at layer 2. So it's actually looking at diagonals. So if that's actually the important thing in the image that you want to recognize, which seems to be the case for this sample set, then we know that at least the focus is correct, right? The neural network is focused on the key thing, which is actually all those diagonal shapes. But if you start seeing that, hey, actually you are trying to detect diagonal shape, but it's actually looking at the edges of the image or the center of the image only, then you know something is wrong and you need to do some, either have more examples to train it better, or you need to reset some parameters for your filters so that it doesn't detect the wrong thing. So with that, we come to the end of this particular series of slides. So I hope this one has given you a quick overview of the difference between especially these key layers, right? The convolutional layer, the rectified linear unit, and the pooling layer, and how that's different from the ones that you typically find in a multi-layer perceptron, which is the fully connected layers. And I also basically want to tell you that you need to be mindful that you need to consider how you would want to debug the training of the neural network, because sometimes the neural network doesn't actually focus on the things that you as a human want it to focus on. Okay, I will see you in the next set of slides. Thank you for your attention.